I work with Henry at the SoC Hub as a research assistant / firmware engineer. My thesis is actually focused on porting Tock OS to one of our first SoC boards. So this presentation is just going to be like an overview of what Tock OS is. Some points might be repeated from the previous presentation. I've tried to keep it as less technical as possible. There won't be any code or any deep technical dive into it. This will be just like a general overview of what the operating system is and what it's capable of and stuff like that. So without any further delay, what exactly is Tock OS? It's the first embedded operating system that's written entirely in Rust. So unlike other operating systems, there's no C or C++ present in Tock OS. It's entirely in Rust. The project actually started as a collaborative research between few universities in the United States, specifically University of Michigan, University of California, Berkeley, and I believe Stanford University as well. It was also used by Google and OpenTitan, and last I checked, Google is actually currently developing their own Rust operating system. And also, the principle behind the development of Tock OS was security. So it was designed with security in mind, and for that reason, the Tock OS actually uses all hardware security features straight out of the box. It uses the Rust programming language to ensure driver security. And there's a separation between the kernel, the applications, and the memory management between the hardware itself. So all of that gives you a very nice, secure operating system. And it's also available in multiple ARM Cortex architectures, and also the RISC-V IMC and IAMC architecture. So there's quite a lot of different boards that you can actually try the operating system on. So here's an overview of the Tock system architecture. So at the very bottom in red, you have the hardware device. So that contains your MCU, your CPU, your timers, ADC, all that good stuff. And then on top of it, you have the low-level drivers. So they basically interact directly with the hardware and expose a hardware interface layer, HIL, to the kernel and everything above it. So the actual kernel, the part you see in the teal color, that basically sits between the low-level drivers and the capsules. The purpose of the kernel here is to provide you with interprocessor schedulers, interprocessor communication, and memory management. And then on the upper part of it, in the blue, we have what we call the capsules. So they're the upper level drivers. And basically what they do is they provide services to each other through the hardware interface layer. And they also provide an API to the user space. So if you need to develop any drivers or something, these capsules provide you with an API to use that. And then at the very top, we have the applications that are written in the light green. So the application, like the previous presenter mentioned, you can write them in any language you want. So it's not Rust. You can write them in C, C++, any language as long as the MCU can support it. And rather than being linked to the kernel, the applications, like I said before, uses an API to sort of communicate with the services from the kernel. So like I mentioned, one of the highlights of Tock is the focus on security. So how exactly does Tock achieve in doing that? So for starters, there's no external dependency whatsoever in the kernel code. So everything you need to know to work with the kernel, that's actually present in the repository. So there's the only dependencies the Tock has is some Rust core library stuff. Other than that, everything you need is there. Another thing is there's no unsafe code allowed in the capsules. So there are instances where the kernel does need to access some memory locations directly by using unsafe blocks. But anything above that, any capsules, any applications that you write, they're not allowed to have any unsafe blocks. If you have any, the compiler is set to reject that code. So if you have any unsafe in it, it'll just outright refuse to compile. So And lastly, applications or services are run in user mode. So basically what this means is, this implies that they cannot access the hardware directly. So they can only access stuff through the API, and they're only allowed to access the memory that they're given, and they can't share that memory with anything. They can't bring down the system in any shape or form. However, to get this feature, this needs to be supported by the hardware. So if you have a platform that doesn't have an MPU or an MMU, this doesn't work. So if you have it, well, it offers this level of protection. And then the next thing is the process memory of how Tock handles this. This is slightly different from your traditional Linux operating system. So first and foremost, you can see that the executable code that's usually goes in the text section in Linux, that's actually located in the flash part of the Tock OS. And that's a read-only part, and not just in name, it's actually a true read-only section. So whatever code goes in there, that's just read-only. And then if you look at the RAM section of it, you can see that it has the heap, data, and stack, but the stack is at the very bottom as opposed to being at the top. The reason for that is this was done to detect stack overflow. So if any application that runs on the operating system and it tries to access a memory section that it's not allowed to, this will enable early detection and will send an error message saying that you can't do it, and it will stop the application from executing. And then at the top, you can notice that there's a grant section. Sorry, so going back with the stack thing, there is a downside of this approach that because you're not allowed to change memory or dynamically grant memory during execution time, every process needs to specify how much memory it needs during compile time, and they have to stick with that one. And also, that means you can't really share your memory space with any other application. And on the top, you have that grant section, and Tock basically uses this to store PCB or process control block, and basically uses this to allocate space for drivers to store their driver-specific data. So for reliability reason, the Tock kernel is not allowed to allocate memory dynamically. That means all the memory used by the kernel needs to be known more or less at compile time. The reason why I say more or less is there are some exceptions to that rule, but it's not very straightforward to dynamically grant them, but you can do it, and it's a bit not very nice to do it. So the way Tock requires this is that each driver has to define a Rust structure. Basically, that structure should contain the data it wants to store and how much space it needs. And the whole process, they just call it a grant. And since there is no dynamic driver loading, the kernel knows exactly how many drivers requires a grant and how large each of these grant needs to be at compile time. Also, another advantage for this method is that when a process is stopped, the memory used by that one is automatically cleared by the kernel, because it knows what particular processes was running and how much grant it required. So once it's done its job, the kernel can automatically clear that. So this removes any danger of leaking driver allocated memories. So now that you have a fair idea of how the memory management and how the architecture works, Tock has a very specific binary format it uses when you write an application. So, and they call it Tock binary format. And basically, it contains an executable code and the initial data, and then it has several headers that gives some information on how this particular application needs to be loaded. And we'll take a look into what that looks like, and it looks like that. So this header files, or the TBF, it basically starts with a TBF header, and it contains information on how an application should be loaded. So because the applications are separate from the kernel, and the kernel has no way of knowing how large an application is, how much memory it needs, or what name it has, we need to solve that issue by adding few headers inside a TBF header of the binary file. So it starts with a TBF header base. As you can see, that one basically contains the version, the header size, and the total size of the file. And then following that, we have a lot of TLV elements, or several type length value elements. And basically what that contains is it contains the type of the data and the length of the said data and the data payload itself. So these basically defines how the kernel should interpret the information from the data, and the length provides the size of the data payload. And that's basically how the whole Tock execution format works. Now, if you're interested in trying to use Tock yourself, it actually does support quite a lot of boards. I couldn't get the full list there, but I would also recommend getting the book, Getting Started with Secure Embedded Operating System. If you can, you should try getting the same board that I mentioned in there. It's a microbit controller and a Raspberry Pi, so one or the other works. The book is a great example of basically starting from scratch. It'll explain every single thing you need to know about the operating system, and you do get a chance to develop some applications for it. But if you're more adventurous, and if you would like to port it to your own platform, there are a few requirements. So first and foremost, memory protection support. This generally means an MPU on a Cortex platforms or a PMP on a RISC-V. This is so that you can run the operating system without an MPU, but that means you lose out on all the security it offers. Also, I guess your port will not be accepted by the official Tock team because they require every platform you run Tock on to have an MPU. And the second thing is that your platform needs to be at least 32 bits. Tock does not work on anything lower than that. And then you also need to have enough memory. Generally, there isn't a particular, like a specific size, but generally speaking, you need at least 64 kilobits of RAM and about 128 kilobits of flash memory to work it. And then there are some generally expected requirements. Like I said, the platform should be 32-bit. Tock at the moment does not support 64-bit, but you can do some hacks to get it to run on 64-bit, like Henry has done it, but it does require some work. And then the platform should be a single core. Your multi-core CPU is fine, but the expectation is that Tock will only be used on a single core machine. Once you have that requirements met, there are some details that you need to be aware of the actual Tock crates itself. So there are three important crates where you need to focus. The first one is the architecture crate. 9 out of 10 times you don't need to do anything to this because it has all the supported code to get this stuff running on any Cortex or RISC-V platforms. So the only time you might need to edit this is if you're trying to run this on a very new architecture, or you might need to make some changes to your MPUs or power management. But other than that, 99% of the time, you don't have to touch any of the code in there. The second thing is the chip crate. That's specific to your microcontroller. So this is where you would implement your chips, UARTs and GPIOs and things like that. So you would basically extend off the kernel hardware interface layer and then just sort of add in the information from your own chip and how things work on your particular chip. And then finally, you have the board crate, which is specific to your physical hardware. And you basically do all your hardware setup in this particular crate. So that includes instantiating the drivers for your sensors, mapping communications, and configuring your GPIO pins. And once you're done that, you're good to go. I have severely made this whole process sound like very easy, but in a nutshell, it's quite straightforward, but in reality, not so much. But yeah, that's that. Anyone have any questions? Oh, yes, great.
Yeah. Can you take back to the architecture pictures with the stack, please?
This?
Yes. So I'd like to understand how the core kernel handles the microcontroller-specific kernel drivers. So assumably those drivers are written in C by the vendor. It goes to unsafe, or are they, like typically all the drivers are written in Rust as well?
The drivers at the lower level are all written in Rust.
Okay.
So like the entirety of the lower, everything up until the top part is Rust.
Okay.
So the whole thing, top to bottom, is Rust, and it's the applications on the top that you have the option to write them in C or whatever it is. because at the end of the day, whatever application you write, they get compiled into that Tock specific binary format that I mentioned, and then it's able to execute that on the platform. Usually once you write an application, you use a Tock loader, a Tock operating system specific loader, which kind of processes this Tock binary format and then does the needed work to get the application running on your board.
Okay. Well, I guess it came from the unsafe allow. So is it accessing any like your firmware or anything like that, or why is the unsafe needed?
The unsafe is so that it doesn't, because you want things to be sort of kept separate, and it's the main focus of making sure that your system stays secure is that the capsules should not be allowed to interface with the hardware directly. It's just so that you can only do it through an API, so that you won't go ahead and start messing with things that you don't have the permission to, or accessing memory areas that you shouldn't be accessing. And the way to limit that is to not allow capsules to have unsafe blocks. With unsafe, you can kind of work your way around it, and that kind of beats the purpose. So it's like you can't do it, and it won't just compile if you write unsafe code in your capsules.
I think the question was, why is unsafe needed for the GPIO?
Oh, the unsafe is needed at the lower level. So there are instances where the kernel has to do some direct interface with the hardware, or look into certain memories. And in that case, it's allowed for the kernel. And it's under the assumption that the kernel knows what it's doing, and everything else. Yes. Sorry.
If I may interrupt, please give a little wave so we can give you a mic, so we can get the questions down as well into the recording. Thank you.
One basic reason to have unsafe code in those drivers is that basically all of the hardware is memory mapped.
Yeah.
So you need some variables that have magic numbers, and then you are dereferencing them as pointers.
Okay.
That's the thing.
Oh, thank you. Yeah. That's not.
There's no risk of the drivers crashing, like that they're protected for that reason.
Shouldn't be. I mean, drivers can crash, but generally speaking, it shouldn't in that sense. As long as you have it right here. Anyone else? Questions? 2, 3, no? Oh, sorry, someone.
Hi. Any insight as to why Tock OS would be restricted to a single core instead of multi-core?
I think they had some issues with inter-processor communication or something like that. At least that was my understanding. I'm not really sure how much progress they've made in terms of that, but I think that was one of the reasons why it was strictly limited to a single core process. We had another question from here. Sure, you.
Hello. Just to continue on the unsafe, I mean, of course, you don't have to write all of the drivers in unsafe code, just put in few lines of unsafe where you need to access the hardware, and then rest of the drivers can be safe as usual.
Yeah, I think I was thinking it more from a Linux kernel perspective, where C is accessed from Rust interface, or the subserver that is fully closed. Then is there like a mechanism in the core kernel that it handles the case where the driver crashes, that the kernel can keep going and doesn't mind about the crashing?
It doesn't mind about that. The grand system we mentioned previously does handle that. If there is a driver that tries to do something weird and it crashes, it'll just quietly take care of it, and the rest of the system can proceed.
Okay, thanks.
Okay, I think there's one noteworthy thing about Tock that is good to remember. The mainstream way to write these applications is with C. The Rust support for writing applications is, I just checked, it was like last commit from August, and the officially tested version of Tock itself was on 1.5, if I remember right.
Yeah, currently.
After that we have 1.6 and 2.0 and 2.1, and it looks sad.
They still have some issues writing the applications with Rust. So currently, most of the applications are written in C with the help of a library they call libtoc-C, which is what you use to sort of help you write these things. Yeah. Any more questions? Oh, there's one more here.
Hi. You mentioned that in Tock, most of the microcontroller-specific peripheral drivers are actually included in the same repo as Tock.
Yeah.
So does this mean that Tock doesn't get to benefit from the rich ecosystem of board and like board-independent support for peripherals that we got to use, for example, in the Rust course at the university?
It does actually. So the way the code is structured is that they encourage you to sort of write it in a platform agnostic way. So as opposed to when you write the code for a particular chip, you're encouraged to do so in the sense that you try and accommodate for that particular family of chips as opposed to just one particular thing. So you do get the benefit of having multiple different features in there. It's up to you which of those features you want to enable or develop further for your particular board. So it's not quite closed off. So I don't have the image here, but if you look through the Tock OS repository, you have different directories for chips, and it contains all the possible variations of a particular Cortex-M family or whatever it is, and then you can extend off of that when you have your own platform in there. So you can pull in whatever information you needed from there as you develop. So it does,
Okay, but you don't get to use, for example, the RP2040 HAL crate that uses the Cortex and whatever HAL crate, and you have to duplicate all that code because it needs to leave.
no, you don't need to duplicate them. You can actually refer to that one, and then it'll still work. It's when we say there's no external dependency, it's specifically for the kernel. The kernel doesn't necessarily interact directly with those chip-specific code. They're using sort of like an API to sort of communicate between each other. There is a very generic sort of, I guess you could say, implementations of like UARTs and SPIs and all that stuff present in the kernel, and then you kind of extend off of that, and then you develop further for your particular chip, if that makes any sense.
Okay. So for the peripheral drivers, you can have things.
Yeah, you can, yes.
Oh, okay.
So what are the performance implications of using Tock compared to bare metal? Like in our application, which is currently in C, C++, we are doing 20 kilohertz loop, running some electric motor algorithms and so on. Is that something that would be feasible on the Tock system, or are the latencies too high or otherwise too much overhead?
I
running
am
this
not
kind of stuff?
particularly sure about that because I don't think we've had any use cases where we've benchmarked performance. So unfortunately, I don't have enough information to answer that.
Okay. So good question then.
Yeah, good question, yes.
Something for you to find out as well.
Yeah. Anyone else? Yeah, that's it. Thank you for your time. Appreciate it.